first one, like me.
But it could be Cal.
So it could be Al?
Al.
It could be both.
Owl 2.
Al too.
Hello and welcome to Calculus2. Settle down, savages. Hold on.
Savages, Indians, comrades.
So,
Demons.
what are we going to do? First lecture. No, it's not a lecture. It's more of a review. We all need to be on the same page in order for you to be successful in Calculus 2. One of the requirements for this class is trigonometry, so we have to review that. The Calculus 2 course consists mainly of two prerequisites, and that will be integration and then limits. So first two chapters, 6 and 7, are application of integrals, chapter 6, and then new integration techniques, chapter 7. And then you hit the two chapters on sequences in series and power series, and that's going to be exclusively limits. Throughout the whole course, here and there, you are going to take derivatives, yes, but primary concern of the course is integration and limits, right? That's most of your class. And then we are going to have a lot of places where trig is going to be necessary for you to go on. We're going to have trigonometric integrals, trigonometric substitution. Trig is going to be a driver in chapter 10, which is prep for your Kalk2. So a lot of trig throughout the course. So I just want to outline certain concepts and ideas that you guys need to know and need to have in order to survive. Starting from trig, right? So what do we have for trig? Well, first off, we have the concept of the Pythagorean theorem, which will be used. That's not trig, but it's going to be used. So a squared plus b squared is equal to c squared. And then if you have angle theta in the right-hand triangle like this, you can write 6 trigonometric functions saying that sine theta is opposite over hypotenuse. Hypotenuse is the longest side in the right triangle. Then the cosine theta is a over c. Tangent theta is opposite over adjacent, so b over a. And now you have the reciprocals of these. So cosecant theta is 1 over sine, which means c over b. Secant theta is c over a. And cotangent theta is a over b. So these are 6 basic trigonometric functions, and these guys, you need to be able to set them up looking at the triangle. This will be very useful when we do trig substitution. So for trig, we are going to also have trigonometric integrals. And for trigonometric integrals, certain identities must be known. The two extremely important identities, which you guys need to use pretty much instantly in class, will be power-reducing formulas. So sine squared theta is equal to 1 minus cosine 2 theta over 2, and cosine squared theta is equal to 1 plus cosine 2 theta over 2. These formulas are extremely important because if you hit the integral of sine squared d theta, the only way to integrate that as of right now is to use this formula. Now, other formulas that are extremely important would be the Pythagorean theorem written in the trig language, which is sine squared theta plus cosine squared theta is equal to 1. I'm not going to go through proofs of these. They can all be derived from the Pythagorean theorem that I wrote with a, b, and c squared, and plugging in these guys in and so on. What's important to know is that this identity will be used a lot, And then other flavors. You can flip this into two other ways, right? You can have sine to be 1 minus cosine squared, and you can have cosine squared to be 1 minus sine squared. So this is technically 3 in 1, right? Because you can rearrange the formula. But you can also divide everywhere by cosine squared and get tangent squared theta plus 1 equal secant squared theta. So you obtain this formula by dividing the upper formula by cosine squared on the left and the right. And we know we're allowed to do that. We can also divide it by sine squared and get 1 plus cotangent squared theta is equal to cosecant squared theta. And those, so each one of these can be rearranged. So technically there are 9 formulas there, right? But they're all obtained from the basic formula here. Now, these formulas will be used in chapter 7. So we'll need that stuff. We also need to know that tangent theta is sine theta over cosine theta, that the cotangent theta is cosine theta over sine theta. So these are our identities for trig. Now, I'm going to put this a little bit aside over here because this is going to be only important for students who want to memorize formulas from the book. You guys will find it a little bit difficult to go back and do the substitution for trig substitution. So trig substitution section offers you to memorize 3 formulas and memorize situations in which you use them and use them. I'm going to teach that section completely different. So if you are embracing what I'm going to teach, you don't need to convert things. But if you go and do what book has to offer, then you will have to use the inverse things. So like this. So let's say you are dealing with sine of inverse tangent of, no coughing, 3 over 5.
What?
Right?
Breathing? Stop.
So you'll need to know how to deal with this, right? And the way to deal with this is you draw a triangle and you say, okay, this is opposite, this is adjacent, so this is 3, and this is 5. So now this one has to be 5 squared plus 3 squared, which is, that's 30 square root of 34. So now we go sine, and then you go inverse sine because they will cancel. But sine is opposite over hypotenuse, so that's 3 over root 34. And now these two cancel each other, and you have the answer to be 3 over root 34. You rationalize that because we are allergic to square roots in denominator, and we get the answer. So, yes. So this witchcraft will be needed if you are going to use the formulas from the book in chapter 7 when we do trig sub. I will teach that section differently than what book has, so you might be bypassing this. We'll see. But the way to compute these things is to create the triangle and then make sure that these are inverses of each other, and then they cancel, and then you go from there. That's the trig requirement. The next part is limits. So limits are going to be everywhere in the course, but they are heavily concentrated in chapters 7 and 8. 8 and 9. 8 and 9. So when you do with sequences in series, every single problem will be a limit problem. and most of them will have also L'Hopital's rule in it as well, which is your 4.7. So what are the ways that well, first off, let's review what is the limit. The way I describe the limit is it's a fancy way to calculate the y value of the function. So if you have x squared and you are observing a certain value, let's say 2, you know that if f of x is given as x squared, then f of 2 is 4. Now this is your pre-calculus. You can also calculate that value by calculating the limit as x approaches to 2 of x squared, and you will still get 4. Now the way these things operate is these two operate differently. So what we have is, when you use pre-calculus, which is the upper calculation, then you start at x-axis, which is your input, and that's 2. You go up or down until you hit the function, and then whatever y value you get there, that's the answer. However, if you are using the limit approach, right, you have to then use this concept, which is approach concept. So you are approaching 2. That's literally like walking on a line. You're walking towards number 2, so your y values will be marching up and marching up as a reflection, right? So as you start walking towards number 2, the y values of your locations here will be marching up the curve, the line, the function, and that in fact will make the y values march towards 4 on the y-axis. From the other side, the blue is also marching towards 2, goes down the function, and then red and blue, I call them Romeo and Juliet, right? If that's not too old of a reference. They would meet at 4. It's like 4 p.m., right? So what we learned from our Calculus 1 is that big theorem which says if limit x approaches a from the left, that's minus, is the same as the limit x approaches a plus, which is from the right, so that's my red and blue, then the overall limit, right, and if those are like limit L, then overall limit x goes to a from both sides of f of x is that L. So this theorem helps you, right? Let me just put otherwise limit does not exist, DNE. So you can see that the limit from the left and limit from the right, as you are approaching 2 from both sides, the y values are marching towards the same value, which is 4. Now that's not true in every case. If you have a situation where limit does not exist, they do not converge onto a same point. So if I have the 1 over x function, and you want to take a look at the limit x goes to 0 for 1 over x, well, look what happens. The red approach from the left is going to have all of the y values march downwards towards negative infinity. And the blue side will have them go up towards positive infinity. And now the left and right do not meet at the single point like they did before, so the limit does not exist. So over here, you had them meet at a single point, limit exists, and it was 4. Over here, they do not meet at a single point. They actually diverge from each other. They go away from each other. And that's why limit does not exist. But it's still the same if you have a piecewise function of some kind, let's say like this. It doesn't matter what you come up with, but it's a piecewise function. So we can actually come up with a formula for this function. That's not that difficult, because you see this is at 2. So we would say that this function, and we know it's a function because it passes vertical line test everywhere, right? So this function has 2 pieces. Terrible. There we go. This function has 2 pieces. The piece to the left is just a constant 2, and that is for all x's that are smaller or equal to 0, because there is a filled-in dot. And then the function is negative x for all x's bigger than 0. Right, so you can come up with a function for this. Now, if you try to find the limit of x goes to 0 for this f of x, the answer is does not exist. Because, and here you go, the limit x approaches 0 from the left of f of x is clearly 2, because this is the y value for the red approach. For the blue approach, from the right, limit x approaches 0 plus of f of x, the answer is 0, because its y value ends up being there. Now, last time I checked, 2 is different than 0, hence limit does not exist because it fails on the theorem. So this is the most basic idea of the limit. Technically, limits computes the y value, unless there is a competition for it. For this particular problem, f of 0 is 2, but the limit doesn't exist because of this jump. The left and right limits do not agree. So now you see that you can solve each limit graphically. You can also calculate values and calculate y values, right, which will be solving it using the chart. But, vast majority of limits is solved either by observing the growth rate of the function or is solved by plugging the value in. So that's possible as well. Now, that works only for basic limits. So x goes to 2 for x squared. Yeah, that's 4 because nothing weird is happening. You clearly cannot do that for limit 1 over x as x goes to 0, because if you plug in, you get 1 over 0. And, right, doesn't work. Now, as you are working with these limits, we are going to have vast majority of our limits in Calculus 2 to be limits that go to infinity. So x goes to infinity. And you might have, let's say, e to the x divided by x squared. Now, the proper way to solve this problem is clearly to do L'Hopital's rule, because when you plug in infinity, you will have indeterminate form, which is infinity over infinity. So, by L'Hopital's rule, we get to take independent derivatives. E to the x stays e to the x, and x squared becomes 2x. Now you still have infinity over infinity, so you can use L'Hopital's rule again. And have now e to the x divided by 2. At this point, you have to stop using L'Hopital's rule because the denominator is no longer infinity. This is infinity divided by 2, but infinity divided by 2 is clearly infinity. So in this case, we had to use L'Hopital's rule twice to come up with the answer. Now, clearly, problem is, what happens if you have e to the x divided by x to 100? Now, there was a theorem in your chapter 2 which stated that the exponential functions grow faster than any type of polynomial function. So by using the growth rate, we can immediately claim that this is infinity, because these functions are not of the same caliber, right? Exponential function grows much faster than any polynomial function. I don't care what power it has. You can put 100 million if you want. The exponential function will eventually catch up and then rise exponentially afterwards and win every single time. This could be turned. You can have limit x goes to infinity of x to 100 divided by e to the x, and you would get 0, still using growth rate of functions. If you want to review this in your textbook, I believe this is with limits at infinity. I believe it's 2.5. I think. I don't know. Might be somewhere else. So we are going to observe growth rate of functions. Now, clearly, if you have the functions that have similar growth rate, or you have the same growth rate functions, you have to do something else in those cases. But, mainly for limits, you hope you can plug in the value. If that doesn't work, then you hope that you can perform some kind of algebra witchcraft on it, which is you can maybe factor or rationalize or do something. And maybe you can do L'Hopital's rule. Maybe you look at the growth rate of functions. So we are going to have some of the proofs in chapter 8 necessary, right, to do. So you guys will hopefully use growth rate of functions rather than doing 15,000 calculations. The next part after limits is integration. So integration is going to be two chapters long. Chapter 6, application, and chapter 7 is going to be on integration techniques. Now, integration in Calculus 2 is going to be primarily U substitution. So if you are not good with U sub, and if you don't learn it very quickly, this course is game over right away. That's technically what it is. Most of integrals in chapter 6 are going to be U sub. That's the only technique you know so far. You should know so far. And then much of chapter 7 are techniques that transform the problem using whatever technique, so that you can use U sub so you can solve the problem. So I would say 90% of your integrals that you are going to see in Kalk2 will be eventually U sub. Eventually, I say. So the reason why the homework assigns 2 sections to you, assigns problem 4.9, section 4.9, which is basic integration, and then section 5.5, which is U sub. Now, I would like to add, so this is on homework, all right, for you. I would like to add 5.3, which is definite integral. Now, that's, you computing the limits, upper limit and lower limit. Now, you don't have to actually work out problems from there, because we are going to have a lot of problems coming up with those limits, so you'll practice that a lot. Especially also transforming those limits when you go. Now let's talk about this integration. Let's talk about the this dx situation. In general, I'm just not allergic to any food. I can eat anything, but I'm highly allergic to people who don't put dx in the integral. So dx is not there for decoration. It actually has a very specific purpose. When you see a rectangle that is A and B, and you are supposed to find the area for that rectangle, what is the formula? A times B. So this A over here, which is the width of the rectangle, is right there. Right? Now, let's jump into Riemann sums and definite integral and all of that good stuff. So say you have some kind of function, blah, there we go, of x, and you want to calculate area under the curve between A and B. Well, the way we did it is you partition this, and then you create rectangles. And now each one of these rectangles has delta x, and it has this height over here, which we call f of xi. Now this I is not imaginary, this I is the location. This is x0, x1, x2, x3, so that I is the counter that goes 0, 1, 2, 3, and so on. Delta x is calculated as b minus a divided by the number of rectangles that you guys want. Maybe 4, maybe 5, maybe 8, maybe 19, whatever amount of rectangles you want. It's fine. So now what we have, if you take a look at any of these individual rectangles, you would quickly see, I hope, that the height of the rectangle is given by f of xi times delta x, which is the width. So this over here is the area of one rectangle. You need to write this in the middle of the page. If you are writing as I'm writing, this needs to go in the middle of the page. Now, I need you to observe this statement and the statement A times B. And I hope you see they're the same statement, except I'm using different variables now. So the function computed at xi is going to give me the height for the rectangle, and delta x is the width. So this is the A times B situation. Now I want to have multiple rectangles, so I'm going to put the sum and say I goes from 1 to n, n being the number of rectangles. As I said, 4, 5, 8, 19 rectangles, whatever amount you want to have. So now these guys together are all rectangles, 1 to n. And finally, at the end, I'm going to add the limit and send n to infinity. So now, with the limit, this becomes what we call the Riemann sum, and this area becomes, so now we have infinitely many rectangles. So what happens when you have that? What happens is you are getting exact area under the curve. So you get exact area under the curve, and we write that as integral a to b of f of x dx. Now what I need you to pick up immediately is that dx and dx, that's the same dx. And if you pay attention in your differentials section in Calc1, you would know that delta x and dx are the same thing. Actually, I'll write dx first. So dx is the same as delta x, and delta x is b minus a divided by n. So that's that one, just written with the D rather than the triangle, which is delta, capital D in Greek alphabet. So there is, on the left-hand side, there is multiplication in between function and dx, delta x. Well, there is also multiplication here in the Riemann sum. So you cannot just drop this dx and not write it. This is not something that is, notation decoration or whatever you want to call it. This is actually the width of your rectangle. So if you do not write dx, you guys are technically saying that the area of the rectangle is height times nothing. This dx is the width of each rectangle. It's embedded in your formula. And now just instead of writing it as a delta x, we write it as dx. Actually, the entire notation is this here. The s, the squiggly sign, is actually s, which stands for sum. And this is sum. So the original notation for integrals, it was s pu, upper limit, lower limit. So you put numbers there, right? That was original notation from 1800s. Over the time, it got changed into what we have today. So the s from the original notation was stretched into this long squiggly line, which we call integral today, and delta x is now written as dx. But that's the same deal. And we also see that, the a and b things that we have here in limits, a and b, those a and b's are encoded in delta x because delta x is a minus b over n. So all of the features of the Riemann sum are obviously there. Now the notation is a little bit different. So now when you go into 4.9 section, right, you learn that the integral of e to the 5x dx is e to the 5x over 5 plus c. Right? You learn that the integral of square root of x dx is going to be integral of x to the 1/2 dx. And now use the power rule, which is plus 1. So that's x to the 3/2 divided by 3, and I'll put half on top, plus c. And others, plus more. Then you go into 5.2. Oh, did I say earlier 5.3? Yeah, it's 5.2, definite integral. All right. 5.3 is a fundamental theorem of calculus. So in 5.2, you get to do the same problem, except now you have limits. So you will find the antiderivative, which is e to the 5x over 5, and then go 0 to 1. You plug in 1 first, you get e to the 5 over 5, and then minus e to the 0 over 5. So now this works out to be, common denominator is 5, and on top you get e to the 5 minus 1. There is no plus c for this calculation, because when this antiderivative was found, and you had plus c there, we don't write it, but you would have a plus c there, there will be a plus c here, and then another plus c here, but this would be in parentheses, so this plus c and then minus the other plus c cancels to 0. So that's why we don't need plus c as we are integrating definite integrals. We only need those for indefinite integrals. So again, plus c is there when you do the integration, because this much of the problem is exactly this. And you see there is a plus c there. But the plus c would immediately cancel in this step, so we don't bother writing it at all. Even though we should, we just don't. So 5.2 gives us to work with limits. But 5.2 gives us actually more than that. We're talking about area under the curve. So now you can go and you can figure out your function x squared, and you say you want to know what is the area between 0 and 2. Well, you will set up your representative delta x rectangle, which we will be sick of by the end of the class. Not class, course. And now you say area is equal to the integral from 0 to 2, because your delta x, which is the vertical representative rectangle, can at most be all the way to the left at 0, and at most be all the way to the right at 2. So those are your limits of integration. We plug in function inside and put dx at the end. So now that's x cubed over 3. Again, plus c, but we don't care. And we get 8/3. So the area under the curve, the exact area under the curve, is 8/3. So I hope you see that this representative rectangle, the dx, is not just something that it's, notational decoration. It's the width of each rectangle that you are adding into area, and it's related to a and a b, because delta x is obtained as b minus a over n. Now, it is important for you to understand that the area integral is a, which is x1, to b, which is x2. So those are just some x values of f of x dx. I can't stress this enough. X, 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 x. They all have to match. Your limits are on x-axis, limits of integration. Your dx representative rectangle and function needs to be in terms of x. That's important. Let's do a very simple problem looking for area of a triangle. So this is at 3, and this is at 7. Great. I'm gonna cheat, put 6 over it. Nah, leave it at 7. It's gonna be disgusting, but such is life. So what is the area here for this triangle? What's the formula for area of the triangle? Well, thank you. So area is 1/2 base times the height, which is 1/2 7 times 3, so 21/2. 21/2 is the area of this triangle. Now I've been painting you a picture. You are tutoring a middle school kid, right? And this comes up, and you say, well, the formula for this is, and they say, why? Okay, here's why. You immediately set up the integral, right? Because the integral calculates area under any curve. So your representative rectangle, delta x, which is infinitely thin. Remember, delta x is b minus a divided by n, and n is going to infinity. What happens with 3 when you try to divide it by infinity? Right, it goes to 0. So delta x is infinitely thin. And if you look at this, the most it can be on the left is at 0, and the most it can go on the right is 7. Those are x locations that track this representative rectangle delta x. So 0 to 7. Now function, well, that's our linear line, and that should not be a problem for us to figure out. We have negative 3 over 7 for the slope, because rise 3, right, and run 7, but it's negative because the line falls. And then plus 3 for the y-intercept. Right, that was quick. It has to go in parentheses. You have two terms, and they both need to be multiplied by dx. So you have to put parentheses around. Now, all I need to do is to integrate. The answer for this better come out as 21 over 2. Otherwise, we're packing our stuff and that's it. Math is over. So, integral, well, copy the constant, negative 3 over 7, and then I have x squared over 2 plus 3x computed from 0 to 7. 0 is going to kill everything, so we don't care about it. But we have to plug in 7. So I have negative 3 over 7 times 49 over 2 plus 21. You see, 49 and 7 cancel to 7, and I get negative 21 over 2 plus 21, which is 21 over 2. Whee! Right? Now, we're not done. Good effort. We can do the horizontal representative rectangle as well. All right? And that one is delta y. Now your integral has to have all y's if you are going to use delta y. Bueno? So, if I am setting up now the green integral, well, now the limits are 0 to 3. Because the lowest the delta y rectangle can be is at 0, y equals 0, and the highest it goes up to is 3. Do we all see that? The limits for dy integral must come from y-axis. Okay. Now we have the problem because our function that we have is given as y equals negative 3 over 7x plus 3. We have to massage this to get x equals everything else. Because, remember, if I am to place a dy integral, the function inside that integral better be in terms of y. So guess what? If the function has no inverse, you can't do it. So not everything can be integrated that way. Only certain problems and certain situations can be done with both dx and dy. And in this case, yes, because we can flip this one around. So I have y minus 3 is equal to negative 3 over 7x. And then negative 7/3 times y minus 3 is x. So now, negative 7/3, y minus 3 goes in here as a function. What's the value of that integral? Just by looking at it, it's obvious. What's the answer? 21 over 2. It has to, because it's representing the same area as previous two calculations. Right? So, and this means? Yes. Because eventually you're going to go home and you're going to look at these notes and then you'll say, well, oh, he didn't do this integral in class. Yeah, because it's going to be 21 over 2. But you can. You kick negative 7/3 in front of the integral. It's a constant. That's y squared over 2 minus 3y. You have your limits. And then when you calculate everything, it's going to come up to be 21 over. So it's a good exercise for you to You know what the answer has to be, and then you just go and make sure it happens. Okay? This is where you're learning, right? Goes. So now, what did I want to achieve with this problem? Well, my job was to find the area of that triangle, right? And we told to that kid, right, well, the formula is 1/2 b times height, so the answer is 21/2. The kid came up with y, clearly regretted his life.
He got more questions now than he did before.
What happened?
He got more questions now than he did before.
That's okay. That's how we grow as people.
Okay.
Like, you know, having questions and talking. So now we have the same area calculated with dx, where I'm using x limit, x function, dx, so x, right? All x across the board, or the green one. If I use dy, my representative rectangles are horizontal. The lowest one is at 0, the highest one is at 3, so my limits are 0 and 3, and I have to flip the function so it's in terms of y and use dy. And as I mentioned, you cannot do this all the time, because for certain cases, your function has no inverse, or a function folds back on itself. What does that mean? Well, we'll see that, because the next lecture will tell us exactly this. You can't use dy in this case, because dy would look like this, and you're subtracting function from itself, and the answer is 0. You see the problem, right? So certain things you can't do. Now we'll get there. That's not it. We're just having the basic thing now with our setup of the integral. So integral calculates area under the curve. And one thing that you have to be very careful about, here's the red flag over here. That's the red flag, okay? I put the spike over here and some blood dripping down. What is the red flag about?
Okay.
It's, yeah, of your grade. You have to be very careful with functions that go below x-axis, because the net area subtracts. So what happens is, you see, when you draw a sine function, right, area under the curve should not be 0 here, right? You all agree that we can color, right? We can color. See that? There's area to be colored. But if you solve the definite integral from 0 to 2 pi for sine x dx, you get 0. You don't believe me? Well, what's the integral of sine? No. Yeah, negative cosine. Good. 0 to 2 pi. So it's negative cosine. And as soon as you plug these values in, you get negative cosine of 2 pi minus negative cosine of 0. And this is negative 1 plus 1. Ooh. Right? That's terrible. Because we can clearly color under the integral, so there is area. But the calculation said, nope, there's nothing there. So we have to be careful with areas that dip below x-axis. So this is not good. It's not good. What we are going to do now is we're going to say, okay, area is integral 0 to pi of sine x dx because that's above. So it's going to be positive. Plus the absolute value of pi to 2 pi sine x dx in absolute values, and that's below. And now when you do your calculations, you are going to get 4. So if you carefully do this calculation, and I'm purposely leaving these calculations out because I did one up there, the second one is going to be the same. Just have to be careful with limits and minus signs. I want you to practice these things because, guys, we have 2 chapters of integration. You have to be good with basic stuff so that we can upgrade this into all possible ways that are coming up in the next 2, I was about to say next 2 months, next 3 weeks. All right? Next 3 weeks, which is your 2 months, right, of regular class. Yeah. 4 letters. So. So that's that. I think we all have a basic idea where we're going, and then we have derivatives. You know, derivatives are going to show up here and there, mainly chain rule, because most of the I didn't talk about U sub. Holy nightmare. Forget about chain. Let's go that. Chain rule. That's derivatives. So the chain rule helps us take the derivative of function composition. So if you have the derivative of e to the sine x, well, that's clearly function composition because function sine x is plugged into the function e to the x, making a function e to the sine x. So when you take the derivative of exponential function, you get to copy that function as is, so e to the sine x, and then you multiply by the derivative of the exponent, in this case, cosine x. If you have the derivative of, let's say, square root of x cubed plus 8, well, the derivative of this is 1 over 2 square roots of x cubed plus 8, and then you have your 3x squared as a chain rule. So chain rule is this extra thing that you get on the side because you had a function composition. You didn't have a vanilla case of square root of x, whose derivative is 1 over 2 root x. I need you to see that the form of the answer is the same. You have root x, root of a function, and you have 1 over 2 root function, 1 over 2 root x. The form of this is the same. However, there is the extra piece here, the chain rule, and the reason why you have the extra piece is because this over here is not x. It's a function. And that part there is the derivative of that function. So that's what the chain rule does. And chain rule can have, multiple chains and so on. We write that the derivative of f of g of x, right, derivative of that is the derivative of f with g plugged in times the derivative of g, right? That's the derivative of the inner function. So you can see that your derivative of f with the g plugged in, and your g was whatever was under the square root. And then here's your g prime. So all of the features of the formula are there. Now, most of the derivatives you will ever take are going to be chain rule. Because how often do you actually have a sine function in application? The answer is never, right? You always have some kind of sine omega t, omega being angular velocity. How fast are things oscillating if you are taking physics? That immediately creates a chain rule. So no, you're not going to use vanilla sine x for anything. You are going to take 95%, maybe even more, 99% of all of the derivatives you ever take are chain rule. Well, what's backwards from chain rule? Which integration technique? It's the only technique that you know so far, and that is U sub. So pretty much every integral you take in this course is going to end with the U sub. Pretty much every single one. All of the techniques of integration that we learn in Calc2 chapter 7 are either U sub on steroids, meaning integration by parts and trig sub, or straight up manipulation of algebra to get the problem so that U sub can be used. We are almost safe to say 100% are U sub integrals. Almost safe to say that. Why? Because U sub for integration is backwards chain rule. So antiderivatives from 4.9, which I'm assigning for your first homework just to practice, it's not calculated, but if you don't know how to do that, you're just done. I'm serious, that's the bottom line in this course. If you can't do basic integration, you're done. So there goes your night tonight if you don't have basic understanding of integration. So my hope is that you are going to go into 4.9 and 5.5 homework and just do 7,000 examples, just to see if you have handle on the basic tool that will be there in every problem.
So we need 7,000 of the basics to know that we understand it.
Yeah. A little bit exaggerated, but you know,
a little bit, like
3K is fine.
Is pretty good too.
So what is the U sub now? U sub integral is going to look for something that you can simplify so you make integral easier to work with. You see, you know how to integrate x to the 6 dx, right? That's simple. But now this is more complicated, right? And in your head you go, well, if this was just like that, it would be easy. And that's exactly what you attempt to do. You say u equals x plus 13 because I don't like it. All right? So now we have to take the derivative over here, right? Du dx is equal to 1, from where we see that du is equal to dx. Oh, great. I can substitute now. All I have now is exactly what I wanted. The problem that had x plus 13 is now converted into just a basic problem, which is u to the 7 over 7 plus c. Don't forget that. And now you have to go back to your original variable, right? Because the problem was posed in terms of x, you better go back to that variable. There's a sentence you can say, I don't care about u, I care about the x. To remember that you have to change this. So here we go, x plus 13 to the 7th over 7 plus c. Do what?
You gotta write sentences on, sentences.
Oh, there will be paragraphs and sentences to write.
This is English.
Yes, which is why I asked.
What?
4 letters. Now, we have more complicated cases. Integral of x e to the x squared dx. All right. It's getting there, right? Getting interesting. you look at this and you say, well, I can definitely integrate e to the x, right? So how about I try to make this just e to the u? See what happens, right? Because I know how to integrate e to the u. So if I replace x squared with u, I will just get e to the u. Awesome. Now, what's the aftermath of this substitution? Well, the aftermath is that we have 2x dx, right? It will be du dx, and you ship dx to the other side. So this is our du. Mm-hmm. And now you compare it. Here is x times dx, and here is x times dx. What's missing? 2. Let's fix that. Plug in 2 and put 1/2 to counter in front. You can only do that with numbers. You can't do that with variables. So now I see that I have 2x dx. So I'm good. 2x dx is du, and I have e, x squared is u. Yay! 1/2 e to the u plus c. I don't care about u, I care about the x. So here we go. Done. Now, I really liked first 2 chapters of Kalk2 because it was integration. Integrals are antiderivatives, which means every time you solve an integral, just check it. You take the derivative. If you get your original problem back, yeah, you're done. If you don't, it's wrong. You see, you can't do that with derivatives, really, right? You take the derivative and, yeah, you hope it's right. You learn some rules and you hope it's right. But you have much more power over your fate with integration. Because if you are not lazy, and if you care, or slash if you care, you can every time go with check. What is the derivative of 1/2 e to the x squared plus c? If it gives you this, and the first test is all integration, you just walk out and say 100, please, right? Because that's that. It's all integrals. So now we copy the constant, e to the x squared. The derivative of the x squared is 2x, and then plus 0, because the derivative of constant is 0. 2 kills 1/2, and there is your x e to the x squared. Right? So you know this is good. And it's going to be left to you as a possibility to go and check every single integral you do in this class for the 2 chapters straight plus 8.5 integral test for series. That's all integration. Every time you do integral, you have the opportunity to check if you care and be done. We have a whole bunch of interesting situations that you can get yourself into. For instance, how about 6 x minus 2 raised to the 3/2 divided by, that's not going to do anything. You can just cancel it. Here we go. Huh. No. The evil and interesting problem I wanted actually can be cancelled. What do you mean A? All right, let's see. That one is not. Oh yeah. Okay. So 6 over square root of x plus 3 dx. right? So if you have this problem, you first rewrite. 6 is a constant. Kick it outside of the integral. Square root is a power of 1/2. So we have x plus 3 to the negative 1/2 dx. Now, u equals x plus 3. du equals, the derivative of this is 1, so du is dx. And just plug in 6 integral of u to the negative 1/2 du, which is 6 u to the positive 1/2 over 1/2 plus c. We just have one more thing after this and we're done. And then we get 12 square roots of u, which is x plus 3 plus c, and we're done. The last concept needed for applied problems in Calc2 and needed for pretty much every integration problem in Calc3 is u sub for definite integrals. Definite integrals have numbers, right? The bound, yes, upper and lower limit. And those numbers need to be changed too. So, here, some bleach.
It says water only right on it.
If you have the integral that is, let's go with sine cubed x cosine x dx. Hello, Trig. Who's happy? 2 of you, nice. From pi over 6 to pi over 3, right? So this is your problem now. Now, when you look at all of this, the best way to solve these u sub problems is to look for what I call function derivative pair. F prime. Do I have a pair of functions that I can plug and populate those? Well, I know that sine is the derivative of cosine, and cosine is the derivative of sine. And there is a minus, but we can fix that. So great, I have both of those present. I have sine cubed, and I have cosine. So if I put sine x here, then the cosine x is its derivative, and this is always u. So let's try this substitution. U equals sine x, du equals cosine x dx. Nice. Look at that. Cosine x dx is right there for us to use. So the problem transforms into u cubed du. How cool is that? Right? We killed all the trig with one substitution. Your sine x is u, and sine x was cubed, so that becomes u cubed. And the cosine x times dx is the du part. The only part that it's left for you to transform are those limits. Because remember what I said earlier with dx and dy. I said x, 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 right? Well, now it's u, so better be u and u over here. And those are not these are x's. So you can't put pi over 6 in these. You have to use your conversion equation, your substitution equation, to convert these into u1 and u2. So what is u1? Let's do it in blood. u1 is going to be sine of pi over 6. Well, that's a half. Perfect. And u2 is sine of pi over 3. That's the upper limit. Sine of pi over 3 is very good. What?
You hear voices. It's not good. Go to Dr. Rob.
Yeah, you sure? I'm never alone. So now we have u cubed. The integral of that is u to the 4 over 4. Calculated from 1/2 to square root of 3 over 2. Now I have 1/4 times. This is root 3 over 2 to the 4th minus 1/2 to the 4th. 1/2 to the 4th is very good. Kick it outside times 4 is nice. And then you have your 9 minus 1, which is, and then when it cancels, perfect. All right.
Hey,
So 1 over 8. I know it goes like this.
teamwork makes the dream work.
True. Thank you for your help.
You're welcome. Always got it.
So this is a problem which outlines the way to change the limits so that you go from your x integral completely into u domain, right, with limits. So it has to be u1, u2, function in terms of u, and then du. Yes? 1 over 16? Yeah. Wasn't it 8 times 8?
64.
64?
I hope so.
9 minus 1. What do you have? Your hands are up.
I remember the negative sign one.
Where?
Because the root of sine is negative cosine.
No, the derivative of sine is cosine. Integral of sine is negative cosine. Well, that's it for today. I hope you're not disappointed. Tomorrow, class preps 6-1, 6-2, sorry, not 6-1, 6-2, 6-3. We'll see. I don't think we can do 6-4, but 6-2, 6-3 definitely tomorrow. We are starting the Kalk2 stuff. So see you all tomorrow. Same room. Hope they keep the air, right?
So for these,